For about 5 years, there was one answer to almost every question about how to make these systems better. More. More text to train on, more chips to train with, more time spent training. Turn all three up together and the thing that came out the other side was reliably better than the last one. That is a strange sentence to be able to write about anything. Most fields do not work like that. You do not usually get to improve something by pouring more of the same into it and simply waiting. But this did work, over and over, for long enough that people stopped treating it as luck and started treating it as a rule. The rule is running out, not because anyone made a mistake and not because the systems turned out to be fake, because the recipe leans on things that are finite and it has started to reach the end of them. Start with what the pattern actually was, because it is more specific than the headline version. Researchers noticed that if you increase three inputs together, the improvement was predictable, not vaguely better, predictable, on a chart, closely enough that you could sketch the next point before you had built the thing. The three inputs are worth separating, because they get blurred together constantly. The first is the size of the model, which is roughly how much room it has to store patterns. The second is the amount of text it reads during training. The third is the sheer quantity of computation you spend pushing that text through it. Turn one up alone and you mostly waste it. A larger model fed the same amount of text does not get proportionally better. The pattern only holds when all three move together in rough proportion. That is the observation. It got called a scaling law, and the name did a lot of quiet damage. Because it kept holding. New model, bigger inputs, better result, roughly where the chart said it would be. Then again after that. When something behaves like that for long enough, people plan on it. Budgets get built on it. Buildings get built on it. You can raise an enormous amount of money on a line that has gone the same direction every time anyone has looked. And this is where the word law starts doing work it should not be doing. A law of nature is a claim about how the universe behaves. Gravity does not get tired. What was found here is an observed regularity. Somebody measured a relationship over the range that was available at the time, drew a line through the measurements, and the line fit well. That is genuinely useful. It is also a description of what already happened, not a promise about what happens next. A line drawn through the points you have says nothing about the territory past the last point. Every observed regularity holds until it meets something the measurements never included, and this one is now meeting three of them. Here is the first, and it is the one that gets the least attention relative to how basic it is. The recipe eats text. Not a specific kind of text, all of it. Books, articles, manuals, forums, transcripts, documentation, arguments, recipes, code. The written output of a species that has been writing things down for a while. That supply feels infinite when you first look at it. Everything ever put online, and more added every day. It is not infinite. It is a stock, like anything you dig out of the ground, and the recipe has been digging in it at industrial scale for years. The easy, high-quality, freely available part of that stock is largely spoken for, not gone, used, already inside the systems you are talking to. And here is the part that makes it worse than a simple counting problem. What remains is not the same quality as what was taken first. Nobody started with the difficult, low-value material. They started with the encyclopedias, the well-edited books, the clean archives. What is left over is thinner. More duplication, more noise, more of the same thing restated badly, and a rising share of text that was itself produced by these systems. At the same time, the doors are closing. Publishers, forums, and archives that were open by default now have licensing terms, paywalls, and blocked crawlers. So the useful supply is shrinking from two directions at once. The good material is used, and the remaining material is increasingly fenced. The obvious fix is the one everybody reaches for. If you need more text, and you have a machine that produces text, have the machine produce the text. Synthetic data, and it is not a joke idea. It is used seriously and it works in specific places. But it does not solve the general problem, for a reason worth being precise about. A model's output is a rearrangement of what it already absorbed. It is fluent, it is often correct, and it contains no new observation of the world. Training on it is closer to reheating than to eating. You can do it. You do not get new nutrition out of it. Do it carelessly and that volume and quality degrades in a particular direction. The outputs get smoother, blander, more average, and the rare edges of the original material fade out first. So where does it actually work? It works when there is a check outside the model. Generate 1,000 attempted solutions to a maths problem, keep only the ones that verify. Generate code, run it, keep what passes the tests. Generate a chain of steps, check the final answer against a known result. In those cases, the model is not inventing new information. It is doing search, and something external is grading the search. The grading is where the value enters, and the grader is not the model. That is a real technique, and it explains why progress in code and formal reasoning has been faster than progress in areas where nobody can automatically tell whether an answer is any good. Which is most areas. There is no compiler for a paragraph about history. That is the first wall. The second one is simpler and less interesting, but it binds harder. Money. The problem is not that these systems are expensive. The problem is the shape of the relationship between what you spend and what you get. Improvement does not come in proportion to cost. To get a step of a given size, you spend some amount. To get the next step of the same size, you spend a large multiple of that. Early on, that is fine, because the steps are enormous and the starting cost is small. The first doublings buy visible, obvious capability. Further along, you are spending an amount of money that would fund a mid-sized industry in order to move a number by a few percent, on a test most people have never heard of. At some point that stops being a technical decision and becomes a question about whether the return exists. Not a wall of physics, a wall of arithmetic, and it arrives sooner. The third wall is the most physical, and it is the one that surprises people who think of this as a software field. Electricity. Training at this scale is an industrial process. It needs a building, and the building needs power delivered to it, and the power needs to come from somewhere that already has capacity to spare. That means substations, transmission lines, grid connection agreements, and cooling, which usually means water. None of those are ordered and installed. They are permitted, negotiated, queued, and constructed. The timelines are measured in years, and they are governed by planning authorities and local politics, not by research. You can write a check for chips much faster than you can get a grid connection. So the constraint quietly stops being the technology and becomes the transformer, the substation queue, the cooling supply, and the local council. 3 walls, then. The material has thinned, the cost per step has grown, and the physical build has a lead time nobody can shorten by being clever. There is a fourth problem, and it is not a wall so much as a fog. It has become hard to see clearly whether progress is even happening. The tests used to measure these systems get saturated. Once a model scores near the top, the test can no longer tell you anything about what comes next. Worse, the tests leak. They are published, so they end up in the training material, and then a good score might mean understanding or might mean the answers were in the reading. So the curve everyone was watching is not only bending, it is getting harder to read at exactly the moment reading it matters most. Now the part that actually happened in response, because the field did not stop and stare at the walls. The center of gravity moved, away from training time and towards the moment you ask the question. The old approach put nearly all of the effort into building the model. Enormous cost once, then every answer afterwards was comparatively cheap. The newer approach spends real computation while it is answering you. It works through the problem in steps, tries several paths, checks itself, and only then replies. That is why some answers now take noticeably longer to arrive, and why the slow ones are often better. And it works, but look at what it does to the economics. The old cost was one huge investment, then cheap answers forever. The new cost is a real charge attached to every hard question anybody asks, forever. That is a completely different business, and it is the reason the conversation shifted from how big is the model to how much does it cost to run. Meanwhile, the less dramatic improvements turned out to matter more than they used to. Carefully filtered training material instead of simply more of it. Better instructions wrapped around the model, giving it access to tools so it can look something up instead of trying to remember it. And compression, taking a large, expensive model and training a much smaller one to imitate its behavior closely enough for the job in front of it. Cheaper to run, narrower, and often better at the specific thing. None of that produces a headline. All of it produces working systems. So what does this mean for the pace of it? Not a stop. That is the wrong picture, and anybody selling you that picture is doing the same thing as the people who sold you the straight line, just in the other direction. What ends is the predictability. For 5 years, better was something you could order in advance. Buy more, wait, receive improvement roughly on schedule. Now the gains come from ideas, and ideas do not arrive on schedule. Progress goes from a smooth ramp to a series of steps of unpredictable size with unpredictable gaps between them. Which is what almost every technology looks like once the first easy stretch is behind it. And the honest fence around all of this, hitting a wall is not the same as being finished. Aviation did not end when propellers reached their limit. It changed method. Every mature field has a moment where the thing that had been working simply stops paying, and the work moves somewhere else. That moment is now, for this particular recipe. The free lunch is over. So the next time you read that a new system is some number of times larger than the last one, you can treat that as what it is, a description of the ingredients, not of the result. The interesting question stopped being how big is it? It is what did they feed it, what does it cost to run, and where is the power coming from?